so today we're going to define a derivative as the slope of a tangent line. And we're also going to extend instantaneous velocity to the more general instantaneous rate of change. Okay? So velocity is how we measure the rate of change of distance versus time. But not all our graphs are distance versus time graphs, so we just use the more generic rate of change. All right, so average velocity is going to become average rate of change. Instantaneous velocity is going to become instantaneous rate of change. And then you can apply those terms to any kind of function, not just a distance time graph. So the instantaneous rate of change of a function f at time t equals a, right, is given by the limit as h goes to 0 of the difference quotient. So I think maybe we should draw a little picture to remind ourselves what this difference quotient represents. So I've got a generic function. And we've got an x, there's an a right there. And if this is x equals a, or t equals a, whatever our independent variable is, if I go a little bit to the right of that, we'll call this point that's a little bit to the right of a plus h. Okay. And then I'll put a point on the graph up here too. Now, if I connect those 2 points with a line, the slope of that line, it's called a secant line, and its slope, we all know how to calculate the slope of a line, change in y over change in x, right? So this first point is, it has coordinates a comma f of a, right? I don't have a formula for f right now, we're being generic. So this is just a function f of x or f of t. And so that point is a comma f of a, whatever you get when you plug a into f. And my second point here is a plus h comma f of a plus h. So if I want to take the slope of that secant line, I subtract the y's, f of a plus h minus f of a, and I divide by the difference in the x's, a plus h minus a, which is just h. Right? So that's called the difference quotient. It's the slope of the secant line, and it represents the average rate of change over an interval h, over an x interval h. All right, and if I wanted to know the instantaneous rate of change at a, I take a smaller and smaller interval between a and a plus h. So I make h smaller and smaller and smaller. So my instantaneous rate of change is the limit as h approaches 0 of f of a plus h minus f of a all over h. That's the instantaneous rate of change, and it is the slope of the tangent line at a. Because as h gets smaller, as this distance gets smaller, the 2 points on the graph get closer and closer and closer to each other until you have a tangent line at a. All right, so we worked through all of that a couple classes ago. Just to remind you, that's what this expression represents. The difference quotient is the slope of a secant line, which represents average rate of change. When you take the limit as the interval goes to 0, that it becomes the instantaneous rate of change in the slope of the tangent line. Okay, so let's do a problem, sort of a real-life problem. The population of China in billions can be approximated by this function f, 1.267 times 1.007 to the t, where t is the number of years since the start of 2000. What kind of function is that? Rate. Exponential. And I heard somebody say it's growth, not decay. How do you know it's growth? Yep. The sort of the base of the exponential is bigger than 1. Yep. 1.007 is bigger than 1. Yeah, or you could call it 0.99 repeating. Same thing. What is the growth rate as a percentage? Close. 0.7%. Yeah, you just got to move that decimal two to the right. All right, so I would like to know the growth rate at the start of 2015 as an absolute amount. So as a different than a percentage, right? I don't want a percentage. I want an absolute amount, like number of people per year, right? Growth rate. How many people per year was the population of China growing by at the start of 2015? So in another way, we want to estimate how fast the population was growing. Rounding is going to be a bad idea, so I'm going to show you a couple little tricks in your graphing calculator. And we're going to give our answer in millions of people per year. So they said estimate, right? So I want to estimate the instantaneous rate of change in 2015. How do you estimate instantaneous rate of change?
F of 15 plus H minus.
Yep. And yes. And without, if you don't take a limit there, that thing is called the average rate of change. Yep. So we're going to take an average rate of change over a small interval. That will give us a decent estimate of the instantaneous rate of change. So we're going to look at f of 15 plus h minus f of 15 all over h. And we're going to pick h to be really small, some small interval of time. And this is going to give us a change in the population size divided by a time interval, and that will give us people per year. All right, what do you want to use for h, small interval?
0.00.
Sure. All right, so 15.001 minus f of 15 all over 0.001. All right, so I'm going to have my calculator hold all the decimals because I don't want to lose anything in rounding error. So I'm going to go to y equals, and I'm going to put in the function. Scroll up so I can see it. Here we go. Okay, so I've got 1.267 times 1.007 to the x. Okay, so I'm going to quit out of there, set it in there. Now your calculator knows function notation, and there's a way to call up y1, and then you just put in parentheses whatever you want to plug in, just like you would write on a piece of paper. Okay? So the way you call up y1 is the vars key. It's right next to clear. Vars stands for variables. We want y variables because we want y1, so you go over to y variables. It's a function. What we're looking for is a function, so you choose function, and then you get a list of all the y's, y1, y2. We put our function in y1, so I'm going to grab y1, and then you just hit parentheses and type in the number you want, 15.001 minus vars y-vars function y1 of 15. Enter, and I want to divide that by 0.001, and I get 0.0098. And what are my units on that? Billions of people per year. Yeah, so that's in billions, so I'll write billions here of people per year. Right, because my function f gives an output in billions of people. Yep. So if I want to change that to millions of people per year, that becomes 9.8, right? 9.8 million people per year. And if I wanted to be even more accurate, right? I wanted to have an even better estimate of the instantaneous rate of change. What would I do? Make h smaller. Good. Make an even smaller h. All right, so if I want to know how fast the population was growing at the start of 2000, we can do something similar. And I'm going to give you 2 minutes to do a calculation on your own. See if you can come up with an estimate. Follow what we did up here. All right, let's go through it together. So this time I want to use the start of 2000, which is t equals 0, right? So I'm going to do f of 0 plus h minus f of 0 all over h. That's how I calculate an average rate of change, right? If I let h go to 0, if I let the h value get smaller and smaller and smaller, take a limit, that gives me instantaneous rate of change. So what I'm going to do is I'm just going to take h to be really small and use that as an estimate for my instantaneous rate of change. Okay, so we'll let h be, let's do 0.01 this time. All right, and then we just will have the calculator do all the hard work. For some reason, the on button doesn't work with the touch screen. All right, bars, y vars, function y1, 0.01. Oops. Minus bars, y vars, function y1 at 0. And I'm going to hit enter here because I want it to do the subtraction before it does the division. So just an order of operations thing. Or you could have put parentheses around that whole thing to make sure it did the subtraction first. So enter and then divided by 0.01. And I get 0.0088. That's billion people per year. So to convert it to millions of people per year, move 3 to the right. And we get 8.8 million people per year. So you can see that from 2000 to 2015, the rate of change increased, right? Went from 8.8 million people per year to 9.8 million people per year. That's a hallmark of a concave up function, right? Which exponential growth is, right? When you're concave up, your rate of change is getting bigger and bigger and bigger.
The rate of change.
Yep. Yep, the rate of change of your rate of change. Okay, so the limit as h goes to 0 of f of a plus h minus f of a over h. That's called the derivative. Okay, so we know it as the slope of the tangent line. We know it as instantaneous rate of change. We now know it as the derivative of the function at x equals a. Note that our independent variable is usually x. We've been using t a lot because we often use time as our independent variable, but we can use a more generic x instead of t. The derivative of a function at x equals a is denoted by this notation, this f apostrophe of a, and you read that f prime of a. F prime of a represents the derivative of f at point a. Okay, so this is our most important definition of the semester. The derivative of f at x equals a is f prime of a, and you calculate it by taking a limit as h goes to 0 of the difference quotient. Finding the derivative of a function is known as differentiating the function. And if a function has a derivative, the function is called differentiable. So these are all phrases that are important, and we'll use them a lot. They'll hopefully become second nature soon enough. All right, so as we've seen, the average rate of change of a function, f of a plus h minus f of a all over h, that's the average rate of change, is the slope of a secant line. And as h goes to 0, that secant line becomes a tangent line. Okay. So we have a little Geometer's Sketchpad animation thing to show you, just to like really drive this home one more time. So I have a function here, pi x squared, and I have a special point and a lemming. Right? So here's my lemming. So right now I'm connecting the lemming and the special point with a secant line. And this program, Geometry Sketchpad, is calculating the slope of my secant line. So as I move the lemming closer to the special point, you can see that the blue line becomes closer and closer and closer to a tangent line. Right? When they're right on top of each other, it's tangent. We often do it to the right. That's sort of more common. So the lemming, so this is going to be point A. This distance from here to here is h. And then we make that distance smaller and smaller and smaller, and we approach a tangent line. Okay. All right. So the Cliff Notes version, the derivative is the slope of the tangent line. In case you didn't hear me, the derivative is the slope of a tangent line. And everybody, 1, 2, 3, the derivative is the slope of the tangent line. Good. All right, so I'm going to let you get started on your activities, do some of these on your own, and I'll be around to discuss. All right, so I want to find f prime of 2. So the definition of the derivative of f at x equals 2 is the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h. Okay. So that's just the definition. Just copied that down from earlier in the notes, replacing the a with 2's. All right, so now f has a formula, right? 1 over x squared. F of x is 1 over x squared. So f of 2 plus h just says go into your formula for f, replace all the x's with 2 plus h's. So this is 1 over 2 plus h squared minus f of 2 is what you get when you put a 2 into the formula, which is 1/4 all over h. And I forgot to write limit. Keep that. You're going to write your limit as h approaches 0 for every step until you plug 0 in. Yes?
So what we're actually going to do, solve all this out.
Yeah. Yes. Correct. Yeah. So if I tried to plug in 0 right now for h, I would get a 4th minus a 4th. So I'd have 0 in my numerator. And then I'd put a 0 in here in the denominator, and I'd get 0 in the denominator. 0 over 0 is an indeterminate form. So when you get an indeterminate form, you just have to do more algebra, right? We want to try to manipulate this thing to be able to plug h equals 0 in. Okay. So usually your goal is to get this h that's in the denominator, this all over h thing. You want that h to cancel. So you just do whatever you can think of to try to get that h to cancel. All right. If this were a problem that I gave you in like a college algebra class, right? And the instructions just said simplify, you would work on this numerator first, trying to get a common denominator. Right? What's the common denominator between 1 over 2 plus h squared and 1 over 4? 4 times 2 plus h squared. Yeah, they don't have any common factors, so you just multiply them together and you get a common denominator. So that first fraction you multiply by 4 over 4. So we get 4 over 4 times 2 plus h squared. And then the second fraction, multiply by 2 plus h squared over 2 plus h squared. All over h. So this is equivalent to the previous one. We just found a common denominator. And the purpose of the common denominator is that then you can subtract the two fractions, right? The new denominator the new fraction, the result will have this common denominator, and then you just subtract the numerators. So this is going to be the limit as h approaches 0 of 4 minus, when I square that out, I get 4 plus 4h plus h squared, all over my common denominator of 4 times 2 plus h squared, all over h. Okay, when you distribute this negative, you get 4 minus 4, the 4's go away, right? Then you continue to distribute and you get minus 4h minus h squared over 4 times 2 plus h squared. And then think of this h as h over 1, right? If you don't like dealing with this complex fraction within a fraction, instead of dividing by h over 1, you can multiply by 1 over h. Okay, this numerator, 4h minus h squared, negative 4h minus h squared, there's an h in each term. Factor out an h. So I'm going to have h times negative 4 minus h all over. My denominator is just going to multiply those together, right? Because when you multiply fractions, you just multiply the tops and multiply the bottoms. So when I multiplied the tops, I got the same thing because there was a 1. Yep, and when I multiply the bottoms, I'm going to get 4h times 2 plus h squared. All right. Anybody see something really exciting? Yep. I have h's that can cancel. Did you have a question? Probably you just missed distributing this negative sign when you subtracted the two fractions. Yeah. So we met our goal, right? The whole goal was try to get the h to cancel in the denominator, right? So I've got h on top and h on the bottom. They cancel. So this is now just the limit as h goes to 0 of negative 4 minus h over 4 times 2 plus h squared. And now that I canceled those h's, what happens if I try to plug in 0 for h? I get a negative 4 on top, right? And on the bottom, if h is 0, I get 2 squared, which is 4 times 4 is 16. No more issues with 0 over 0, right? I can just plug in my 0 now. And that is negative 1/4. There's a lot of steps there, and some of those steps I did like two things in one. So I definitely would recommend going back and trying to redo this by yourself and make sure that this all makes sense to you.